Indiana Public Library and to one of the programs of our Science Riot. I'd like to tell you a little bit about Science Riot. If you've not been into the auditorium today, or if you hadn't been in yesterday, please make it a point after this show to go down to the auditorium on the main floor. We have several exhibits down there that are science-oriented, and they are from organizations or industries in the Fort Wayne area whose product or service is of a science-related subject. So make sure you get down there to see it if you can. We also have at the base of the stairway in the Renaissance Center for the Book a collection of science books and an exhibit of some memorabilia with science. It's right under the dinosaur that's hanging from the ceiling. So make sure you get down there and have a look at some of our materials. We felt at the library that it was time to highlight our science collection, and we thought if we had a science riot that was something that would be exciting and stimulating, that it would attract people to come down here and see what science is all about and how it touches your daily lives. And as a part of that, we also have films in children's services, so you can go in and see anything about science in a film structure in their room all throughout the rest of this day. The auditorium will be open throughout the rest of the day during library hours. Without further ado, I would like to present to you today Dr. Allan Longroy from IPFW. He is a chemistry professor at Indiana Purdue out there, and he has a really spectacular show for you to see today. There are a couple of things I'd like to ask of you. Because we have a very small room and lots of people in it, I would like you to listen to what he talks about and respond to it, but don't do lots of talking in between, because he's going to continue on talking without a microphone, and you may miss some of the important information that he's going to give you. It's really worth your while to listen and tune in carefully. You're going to, what I would say is fasten your seatbelt, sit back, watch a little bit, and learn some things. So without further ado, here's Professor Longroy.
Thank you, Cheryl. I should perhaps introduce who's helping me today. Monica Committee is helping me today. We have a standard joke that I'm doing so many things here and using so many solutions that are unstable that anything can go wrong, and if it does, I blame her. That's one of the reasons why she's also a great asset for the show. What I'm going to do is to show you a series of demonstrations in the sciences and in chemistry. I'll be doing a variety of things. I'll be mixing things together and doing things. What happens typically is fairly fast. The demonstrations that are in the show are fast because we want it to be kind of lively. In some cases, but not all, you will find surprises perhaps. And to that end, sometimes the show, most often as a matter of fact, the show is referred to as chemical magic. Some of the things I'm doing are really not that scientific or spectacular, but they're fun to do, and I hope you enjoy them. I hope you enjoy the whole show. I hope you learn some terminology, perhaps learn some chemistry, and maybe go home with a feeling that the sciences really aren't all that bad. Some people think they are, but it's really not all that bad. I'd like to begin with a demonstration involving an element. The element is phosphorus. It's in solution. I've dissolved a little bit of phosphorus in this solution in this container right here. And what I'm going to do is to write with the solution. We constructed what I refer to as a magic marker, and it's really pretty simple. It's just a pipe container and a piece of glass tubing. And that's to protect my fingers, and you'll see why as soon as I've written something out. Now, this is going to take me just a couple of seconds to do this. And I'll show you what I've written, and in so doing, show you the properties, one of the properties of the element phosphorus. And here we go. I want to get the magic marker so it's also the same thing. What you've seen is an example of one of the properties of phosphorus, and you might refer to this as being spontaneous combustion. Or for those of you that are younger, it burns by itself. We're going to start a series of demonstrations with nitrogen, and I'd like to preface my remarks on where nitrogen comes from. You should know that nitrogen is the major component of the air. It's about 78% of the air. The air is about 20% oxygen and a bunch of other things. We've got carbon dioxide and moisture and quite a bit of argon, as a matter of fact. If you take air from any source, of course, it's all over the place, cool it down, put it under sufficient pressure, you can get a product which is called liquid air. If you take the liquid air, you can separate it into its components, and of course the major component being nitrogen. Nitrogen boils at 320 degrees below zero. It has to be kept very cold. We have it in special equipment here. This is a special brewer flask. We use this for transporting the liquid nitrogen. It boils at 320 degrees, so anything that hits, which is hotter than that, causes it to boil. Now I'll pour a little bit on the floor here, and what's going to happen is it's going to go scurrying around. And the process of scurrying around, of course, why it's doing that is it's boiling, of course. I like to use the analogy of a red-hot stove. Kind of like pouring water on a red-hot stove. It scurries around. But again, you should be reminded that the nitrogen, liquid nitrogen that we're working with here, is a boiling point of about 320 degrees below zero. Okay, let's do some things with it, and to do some things with it, we need some equipment. I'm going to pour some into this flask here. This is also a Dewar flask. This is a large Dewar flask for transporting it. This is called a wide mouth Dewar flask. I poured it in here, and it's boiling away in there because the flask is hot. It's been sitting here for some time. It won't take very long before the inside of the flask is cooled down to about 320 degrees. You can see it settling down. The liquid nitrogen will start to hiss. It's hitting there right now. And it won't boil so vigorously because it's down to about 320 degrees below zero. Well, what we're going to do is to put some things in liquid nitrogen. And again, this isn't really that fancy, but I think it's fun to do, and it might be appealing for 320 degrees below zero. The first thing I'm going to put in there is a flower. This is a carnation, and it doesn't have much mass. Putting it down in liquid nitrogen, of course it's at room temperature, it causes the liquid nitrogen to boil. In the process, it's cooling the flower down to 320 degrees below zero, and it doesn't take very long. You should realize, of course, that this is a biological entity. It has water in it. And you know that if you take water from its boiling point, which is 312 degrees down to 32, it freezes at 32. And in this case, we're taking it down 320 degrees below zero, so we're much below its freezing point. The properties are going to change, and with that preface, you probably have an idea of what's going to happen. 320 degrees means the water has frozen inside the flower, and where it was pliable before, it's kind of like Wheaties now, kind of like corn. There goes the flour. We're going to put some other things in here. Well, I guess I should tell you what we're working with here. This is a piece of rubber tubing. We use rubber tubing in the laboratory for transporting gases and liquids. We're going to cool it down to 320 degrees. There's not much mass here, so it doesn't take very long to cool it down. It takes just a few seconds. And you'll hand me a bucket. I'll take the rubber tubing out and put it around the bucket. And you can see, and probably you're not too surprised, cooling rubber down to 320 degrees below zero changes its properties. It becomes stiff. And as a matter of fact, you can see the surface of the mercury where it was dropped down, or the mercury, dropped down inside the liquid nitrogen. Okay, well, we're going to put some other things in here. Here we have bracket balls. You might have an idea of what the properties of these things are like. When you get a chance. There are properties that you're probably familiar with balls. And we're going to change the properties of one of the balls by cooling it down in liquid nitrogen. That's going to take a few moments for it to cool down. There's quite a bit of material there to cool down. And along with it, what we're going to do is put something else down that you're familiar with. This is a banana. You know what the properties of bananas are. And I'm going to stick one end of it. Actually, one end of it is going down in liquid nitrogen. And it takes these things a little bit of time. A banana is quite large. It has quite a bit of mass associated with it. Or there's lots of water there. So it's going to take some time for it to get down to temperature, down to 320 degrees below zero. While it's cooling down, we'll move on to the next demonstration, and also involving a dewar flask. This is another kind of a dewar flask. It has a different kind of an opening because we're going to do something different with it. It's constructed in the same way as the others are, but it's perhaps better to see. You can see there's an inside container and there's an outside container. It's constructed by adding the outside container last. There's a seam going around here. It's expensive because of that reason. There's a knob at the bottom, and what's done is this knob is attached to a vacuum pump, and that sucks all the air out. There's a vacuum space in between the two containers there, and of course that slows down heat transfer. We're going to pour some liquid nitrogen in here, and to do that, there are a couple of problems. One is it's a small hole, and the other is it's hot. This is kind of like a red hot stove. Low temperature compared to the liquid nitrogen. Of course, it's real hot. When the liquid nitrogen goes in there, what's going to happen is it's going to start boiling. It's going to start shooting out the gas. And I'm going to try to get some in there, and it's going to go all over the place. But we get some down in there. That's not bad. Whoops. And there's liquid nitrogen. You can see it boiling in there, and it's giving off nitrogen gas. It's getting off a lot of nitrogen gas. That's a big breath, isn't it? There's a lot coming out of it. And I'll swirl it around. Boy, it's really hot today. I'll swirl it around because I want the inside of the flask to get real cold. And I want as much of it down to about 320 degrees below zero as I can get. And you can see it settling down. There's not as much gas coming out. The temperature on the inside of the container has dropped. We're going to attach it now to a vacuum pump. Remember, the vacuum pump was attached here before it was sealed up. There's a vacuum in between. Now what we're going to do is to add this gadget to it. That's why we're using this equipment now, is because we want to pump on the liquid nitrogen which is in there. This is called a stopcock, and all it is a valve which, turned like this, closes up the equipment. If I swirl it around, the nitrogen, of course, in there is boiling, but it's got no place to go. And of course, I'm hanging onto it so it doesn't blow off. But there's not much pressure in there because there's just a little bit of a gush. There's not much pressure because it was pretty much down to temperature. We're going to pump on this now. We have a vacuum pump set over here, and Monica is going to turn the pump on, and we're not right now. Oh, yes. And we're going to pump on it, and it's going to take just a few moments before this is done. What reducing the pressure on the inside does is causes it to boil. You know, perhaps, that when water evaporates, when there's water on your skin and it evaporates away, you feel cool. And there are two things involved there. One, we call them kinetic energy. We call them kinetic energy. There are hot water molecules and cold water molecules. The hot ones are the ones that tend to be lost first. Those are the ones which have the highest kinetic energy. And at the same time, it takes energy to go from the liquid state to the gaseous state. So what happens is the temperature drops. For water, your skin feels cold. And here, what's happening is we're dropping the temperature on the inside of the container. We're pumping out the nitrogen. We're pumping out the hot nitrogen molecules, which are only 320 degrees below zero. And what's happening is the temperature is dropping, and it's going down. You can see there's a change going on the inside. If it were water, starting at the boiling point, which is where we started, water would have to go from 212 degrees Fahrenheit down to 32 degrees Fahrenheit before it freezes. For liquid nitrogen, we start at about 320 degrees below zero, and we have to go down about 16 more degrees is all. Also what happens is the liquid phase in here. The liquid state has more energy associated with it, so the molecules tend to come, the warmer nitrogen molecules tend to come from the liquid phase than from the solid phase. And it's just about done. And let me see if I can turn the stopcock. Can I tell you? Okay, Herman. Whoops, there you go. So we cool down a sample of liquid nitrogen down to its freezing point and have a sample of solid nitrogen. Now remember when I started the discussion, I told you and reminded you that nitrogen is about 78% of the air, so you might consider this a solid chunk of air. Of course, it's shaped like a snowball because of the container that it was formed in. What I'm going to do now is to open up the stopcock. It's under vacuum, see? So when I open up the stopcock, it's going to drag air in, hot air, and what happens is, you should be surprised at, we refer to this as, of course, if you want to be fancy, we call it a phase transition. You might want to call it just melting. That's really all it's doing. We call it a phase transition or change of state. That's a scientific way of saying it. You've seen, then, the change of state from solid nitrogen to liquid nitrogen. We've also picked up, it's a little bit cloudy in there, and a little stuff floating around in there. There's probably some moisture or some carbon dioxide that we've also picked up. And we've been boiling it, of course. And let me pour a little bit on my hand. Nitrogen, of course, boils at 320 degrees. My hand is like a hot stove. And my hand offers a little bit of protection because it's red hot compared to the boiling point of nitrogen. So what happens is there's probably a cushion of nitrogen that protects my hand. But I wouldn't leave my hand associated with it for very long because it would become like the banana. And the banana, I think, is done. Remember, we put that in there just a few moments ago. And let me frost it up a little bit. You can see where it was down in liquid nitrogen. The properties have changed. You probably have an idea of what the properties are like. And what I'm going to do is, with a block of wood and a nail, there, I'm a carpenter. The nail's in pretty good. One end, of course, has been frozen in the liquid nitrogen. The other end was kind of sticking out. It's a little bit cool, but it's really not that cold. And it's still a banana. I haven't had any lunch, so I'll take a couple breaks as we're going along to show. This is the first lunch break. I also like them when they have those little sugar spots on them, speckled with black. Well, we're going to get rid of this. For those of you that have experience in freezing fruit and thawing it out, you know that it gets mushy. And we've learned that a banana gets real mushy. If we left it on the table, we pick it up with a spoon. It gets that bad. Well, we still have a ball. Remember, we put a racquetball down in here. And since all of that is cold, I'm going to protect my hands with a glove. And pull it out with these forceps, and I'm going to bounce it on the floor. Now, you've seen it bounce before, but I'm wearing a glove, and none of you kids here have a glove on, so if it bounces towards you, don't catch it, because it's cool.
Ding dong. They ripped you off.
And you probably had an idea that it's cold. I mean, you probably really weren't that surprised with what was going on here. And now I'm going to do something else with something that you're familiar with. The reason I've blown it up is because I want for you to know what's in there, that this isn't some other gas that's in there, but it's mostly air, mostly nitrogen, oxygen, I've used up a little bit, contributed a little bit of carbon dioxide, and banana flavor. What we're going to do with this is cool it down to 320 degrees, and you don't really have to have too much experience to know about some of the properties of gases. One of the properties being that as you cool a gas down, it shrinks, and as you warm a gas up, it expands. Only now we're cooling it down to 320 degrees below zero. And even though you kind of expect what was going on in the other demonstrations, you might be surprised that we can shrink this sample of gas down, the sample of gas being held in a balloon, down to 320 degrees. And it shrinks down to just about nothing. It's so cold that the gas goes down to just about nothing. Out here, of course, the air is hot, and what happens is the gas starts expanding. And it looks funny. Usually there's somebody with their fingers in their ears thinking that it's going to explode, and it usually doesn't. Every once in a while it will break. And well, there's just a little bit of a puddle left. And let me do it one more time. I think this is fun to do. And let me do it one more time and point out the puddle that's down in the bottom. Remember, air is, well, the air that we have in there has mostly nitrogen. Oxygen is the next component. And oxygen boils at a higher temperature than does nitrogen, so it's the last thing to come off from the sample. And Carmen has been taking, maybe you know it, Carmen, Monica has taken the liquid nitrogen over there to cool down some oxygen. I'll say a little bit about that in just a second. Right now, I'd like for you to see there's a puddle. Can you see the puddle down in the bottom? There's a little bit of a puddle. Oxygen boils at a higher temperature. The nitrogen goes up first, the oxygen then comes up second. That's how the separation is done. If you cool air down, you can make the separation by distillation. Now, she's been putting liquid nitrogen in that container on the end. There's a large, well, not that large, gas cylinder. It's a cylinder of oxygen. We're bleeding the oxygen from the cylinder into a container which is cooled down with liquid nitrogen, and cooling the oxygen down to make liquid oxygen for a later demonstration. Next, this is also a gas, and when I go to schools, a lot of kids have seen the use of helium, and what I'm going to do is exactly that. I'm going to breathe in some of the helium. I've got just a piece of rubber tubing in there and a test tube in the bottom so I can get it apart real easy. And what I'm going to do is to talk as I have been, and it's going to come out different because of the helium's effect upon the voice. Now, I'm going to say something, and then I'm going to take a breath, and I'll try to take just a little breath so I dilute the helium just a little bit, and so on. You can hear the helium being dispensed with as I go through each phase.
Where, oh, where is the wicked witch of the west? Where can she be? I'm going to have to take a breath.
There came the breath, and you could hear just a little bit of a difference in my voice. And here comes the next breath, and it's just about back to normal. And one more breath, and it's all gone. Now, what happens is, of course, the helium has an effect on the voice, and it's a perfectly safe gas. It's used in deep sea diving. Maybe you've heard of nitrogen narcosis or rapture of the deep, some of those things. Helium doesn't dissolve in the blood, so it's a safer gas to use for the deep sea divers. At the same time, doing the demonstration, I'm without air for that period of time. I get a little bit dizzy. And there's enough here if we have a parent which will volunteer a kid or something.
I would.
Or somebody. I guess I have to choose somebody. Somebody that's handy. Here's somebody handy. Here. You're going to be in show business. What's your name? You have to tell everybody what your name is and how your voice sounds before we do this. Kimberly, where do you live? Fort Wayne, Indiana. Mm-hmm. Where do you go to school? St. Paul. Have you done this before? This is a new experience. I'll let you squeeze the balloon there. That's up against it. And before you do it, let me remind you what you're going to do. You're going to take all the air out of your lungs, blow out everything that you can, breathe in as much helium as you can, and then you have to say something. Have you ever got something to say? How about singing? Can you sing? How about a nursery rhyme, a poem? You have to think of something to say, otherwise. What is it? It's going to be hot, yes. Can you have something to say? Okay, that's good. Exhale. Talk. Well, thank you, Kimberly. Give her a hand anyway. We're going to do a series of demonstrations now in the liquid phase, the liquid solution chemistry. The first demonstration starts out with a solution of an indicator dye in water. We call that an aqueous solution in sciences, rather than saying it's just dissolved in water. And this has an indicator dye in it, which can be changed by an acid or base. That is, it indicates the acid or base nature of the solution that it's in. So we have an acid solution and a base solution. Each of them is a dropping container, like it has nose drops. And that way I can control. I can put one drop in there, give it a swirl, and you can see the effect of acid on the indicator. Now, this is a reversible indicator. One drop, this is base, one drop of base will make it go back to the other color. And a drop of acid will make it go back again. Just add the drop, mix it up, and it's done. And we can go back and forth. It's said to be a reversible indicator dye. And we can do that all the time, but that's enough of that. We're going to get more sophisticated fairly rapidly. This is another solution of an indicator dye, a pH indicator dye, and a little bit of base in there. You can, well, it wasn't quite enough. You can see that it's a different indicator dye because there are different colors. It's also reversible in that a drop of acid will make it back to the acid form, and we're right there right now. So a drop of base will get it back to the basic color. And what I'm going to do, remember now, acid makes it the yellow, orangish color. The base makes it, well, it's green right now. I'm going to add more base to it and mix it up. And there's a blue color. It's a nice blue color which is associated with it. Now remember the colors combination and the excess of the color I've got in it. Right now it's got excess base in it. I'm going to add something else to it now and mix it up. Just add to it, mix it up. That's what I've been doing, is mix it up. Uh-oh. Uh-oh. In fact, there's something which is going on. It's still a basic color, isn't it? Are you all with me? But what's going to happen is it's going to change. And I hope it does pretty quick because I've run out of things to say. There it goes. It turned green and then the yellow. Now, what form is it in now? That's the acid form. And let me add a little bit more base and we'll get it back to the basic form. That's the basic color, which is a blue. Now, what happened before was it turned the other colors, and here it goes again, and changing to the acid form, so you should rationalize from that there's an acid being produced in the reaction in the container itself. And in fact, that's what's happening. Acid is being produced all the time. When I make it the basic solution, that takes it back to the basic side. The acid is still being produced and leads to the production of the acid condition. The name for this demonstration is called an oscillating clock reaction. I'm ahead of myself today. That's coming later. This is a rainbow clock reaction because of the colors that it goes through. It starts with the blue end of the spectrum and goes through the rest of the colors for the spectrum. It's a clock reaction because it's time dependent. see more, you'll see an oscillator clock later on in the demonstrations. Next, we have the preparation of a compound that you're perhaps familiar with. Could be. This is a form, however, which is not commercial. It's nice for the demonstration. It involves two solutions. There's one solution in there, and I'm going to add to it another solution. These are said to be immiscible. That is, one doesn't mix with the other. It's kind of like oil and water don't mix. And I'm going to run this right down the side and try to avoid as much mixing as possible. And if you see down in there, you can see something is happening at the where the two solutions come together. You can see one solution is a little bit yellow on the top and a clear solution on the bottom. At the interface is something which has been produced. I like to refer to the analogy. We always use analogy as we always use food as an analogy in chemistry. That keeps the students' interest aside. I like to use egg drop soup for this analogy. It's kind of like egg drop soup. I'm going to reach down in there and grab it. And pull it out. The compound that you're seeing is commercially called nylon. So you're seeing nylon being made in front of your eyes. What's happening is there are two solutions, each one of which has a reagent. The reagents, when they get together, react to form nylon, and as we pull the nylon away, that allows more reagents to come together, and that's why we've got this contraption set up here. And we can make a few cranks there. Again, what's happening is there are two reagents, one in the bottom, one in the top layer. They form nylon when they come together. We're dragging it away. In the process of dragging it away, there are fresh solutions which come together to form more nylon, and we get the rope, it's called. It's called the nylon rope trick. We've done one clock reaction, the rainbow clock reaction. Clock reactions are time dependent, as you observe. And we have this clock reaction. This is a different clock reaction, which is set at 3 times. They're all the same right now. And to emphasize the fact that it's time dependent, what I'm going to do is to mix the two solutions together and then count. 1001, 1002, 1003, 1004, 1005, 1006, 1007. This is a double change clock reaction. Those are Purdue's colors, too. I always put that out. To emphasize the clock nature and the reproducibility of what we're doing here, I'll do it again. 1001, 1002, 1003, 1004, 1005, 1006, and that one's up to be Purdue. And the last one we'll do a little bit different. We have a container here that we're using it to clean out our equipment and stuff, and all it is water, see? It's just water which is coming out of here. What I'm going to do is to dilute one of these systems. And not knowing any chemistry, there might be a couple of things that you might have a feeling for in terms of how fast reactions go. You might know that if you heat things up, things go faster. And of course that's shown in chemical reactions. But that's hard to do. To have these two solutions and heat them up would be an effort for me to do here. It takes some time. Diluting it was very easy. And you might have a feeling that if you dilute things, they go slower. And that's what's going to happen. Let's do it again. 1001, 1002, 1003, 1004, 1005, 1006, 1007, 2008, 9, 10, 11, 12, 13, 14, 15. And it took a significant longer time before the reaction was done. Okay, Purdue. But I suspect there are some IU people out there. And we have a way of taking care of the Purdue colors. It takes care of one Purdue and another Purdue and Oh, there goes the third. I like to run out before the last one is done and then say, you know, you can't get rid of Purdue, but you just do it. Next is a demonstration involving, well, maybe you've heard of the old stories about the alchemists and changing base metals to gold. And I have a secret. And what I'm going to do is to show you how to do that, starting with pennies. And what we're going to do is to put them in the container here. There's a beaker set up with stuff, and we're going to drop some pennies down in here. And it's going to take a little bit of time. I mean, making gold out of pennies, you know, can't be that fast. So this is a little bit of effort, and what I'm going to do is get this started, and then Monica is going to control the reaction. We have to heat it up. We have to boil it for a while, as a matter of fact. It's going to make a little noise, too, so I'll have to talk a little bit. What we're going to do is to just heat it up and boil these things together, and there's something which is going to happen to the penny, but we won't be done. Maybe. That should work. I'll let Monica do it while it's going. And while she's doing that, I'll try to talk over it. I don't know, it must be the liquid is coming out. It's a new container. Try to keep it up there. While she's doing that, we'll go on with the other demonstrations. And this one is a very simple one. Everybody knows that chemists can make things explode. And I'll let you fight with it. Lots of luck. I brought with me a material. The compound is called nitrosoguanidine, and none of you will have ever heard of that before. But it's used. My understanding is it's used in the theater for making smoke. And it turns out to be a fairly nice compound. And what I'll do is to put a little pile of it here. Get down below. Get the flames up one second. It's a new gas bottle, I think. And some of the liquid is apparently blowing away. Well, we have a little pile of this material right here. It's a nice material because it does its job, and I put it on the paper. This is a paper outfit up here, and I guess I should point out that we've got the fire thing covered up, the smoke alarm covered up, so if anything goes wrong. That's what's in there. It's a neat material. There's no residue. It's kind of a nice thing to do because of the residue not being there. Gunpowder or something like that, of course, it's going to be missing. Well, there's energy. That's how we're starting this series of demonstrations. There's energy in that sample. We've brought in some other things that have energy associated with them. This is a tube of benzoyl peroxide. The compound is called. Benzoyl peroxide is used commercially as an ingredient in a medicinal. Maybe you've heard of Oxy-10. If you're a teenager, it's probably more important to you because it's used for removing zits. Oxy-10, I think, implies that there's about 10% solution of benzoyl peroxide in it. And they used to advertise the fact that they had benzoyl peroxide in the material. What I'm going to do is to put this benzoyl peroxide and show you one of the other properties of benzoyl peroxide. It's also a very powerful oxidizing agent. It's also used for catalyzing polymerization reactions, for making plastics and things like that. But I'm going to show you the oxidizing properties of it. This is a beaker with a piece of paper towel in there to hold the tube up. What I'm going to do with the very powerful oxidizing agent, benzoyl peroxide. Let's add something to it, which is very easily oxidized. Just a couple of drops. And when a very powerful oxidizing agent gets in the presence of something which is very easily oxidized, there's a reaction which looks like this. I said it looks like this. There. You didn't need a match for that. Are they done? Okay. Let's see. We got new pennies for this, and to show you the difference so far, here's the new penny right here, and here's the penny that we've modified. And it looks like silver right now. We buy that I've gone part of the way, at least, in converting a copper penny to a silver penny. That's at least the value of some. What I'm going to do now is to heat this up. And let me hang on to it right here. And if you can see from where you are, I'm going to heat it up. And it's going to change to gold. Can you see that? Now gold. Let me cool it down. Whoops. Well, it didn't quite get done. Let me pull one of those out. I'll show you the 3 stages. This is the new penny. And in my fingers, well, there's the silver one. And I'll cover up the blemish on that. We didn't quite do it right. There's the gold penny. Now, I propose that I'd like to start a business here. I'm looking for investors. If you'd like to invest in my process for $10 cash, I can continue working on this, and maybe we can all do this. Line up after the show. Well, let's go. We're involved with compounds which have energy in them. This demonstration involves 2 solutions. This first solution doesn't have energy in it, but it's something that you might be familiar with. This is a calcium salt. Calcium is used for teeth and bones. That's why you drink milk. This is a solution of ethyl alcohol. Well, it is ethyl alcohol, 95% ethyl alcohol, which is the kind of alcohol that shows up in beverages and stuff. I'm going to mix these 2 things together. And there will be a reaction. And the properties have changed. The calcium solution, calcium acetate solution actually, and the alcohol solution, the properties have changed where I had 2 solutions going together. I now have a solid sample. What I've prepared is a compound that you might be familiar with. The compound is sold commercially as sterno. It's kind of waxy, jelly kind of material, and has energy associated with it. What I'm going to do is I put that little piece in there, and I'm going to ignite it. And to ignite it, I'm going to use a magic wand. And with my magic wand, I'm going to ignite a candle. And with the candle, I'm going to light the alcohol. And there goes the alcohol. And let me point out to you why alcohol was used in gasohol. Not too long ago, it was advertised quite heavily as being one of the ingredients in gasoline to cut down on pollution pollution problems and preserve with a nice clean flame. For those of you that have used sterno in camping, or maybe you have a fondue set in which you use sterno, the idea there is, of course, that the solid material, if you knock it over, if your fondue set is knocked over, there's not flaming liquid all over your dining room table. There's a lot of energy in this, and for the kids, let me show you how much energy there is. And if you're familiar with the material that I'm adding, of course, it's used for making fireworks. There's energy in ethyl alcohol. Here's a container which has ethyl alcohol in it also. We're going to take just a little bit. This is in a dropping tube, a dropping container, so we can take just a little bit out and put it in there. And let me point out to you what we've got here. This is a plastic container. It's got some tape around it and a wire coming out. On the inside, that wire comes in, just about touches another wire on the inside. And I just put some ethyl alcohol in there. And I'm going to close this up. And you know, of course, that ethyl alcohol has energy associated with it. The wire comes out, and to show you this is going to be involved in this demonstration. This is called a Tesla coil. It's plugged into the house current. As I turn this knob, that increases the voltage on the inside of the contraption here. This is a very high voltage. Can you move back a little bit? This is a high voltage thing, and maybe you can hear it arcing here. But we have a neater way of doing that. This is called a discharge tube. And we use them for an experiment in general chemistry at the university. And there's a lot of energy in this thing. Touching this thing makes it light up. What you're seeing is a neon discharge tube. That's the color of neon, which has been, discharging. Now, if you put all this together, we've got in here alcohol, which has a lot of energy associated with it, in a container, sealed container, with a wire going through and just about touching another wire. If you put all that together, you know what's going to happen when I touch this thing. Wake everybody up. Jose. Were you surprised? There are.
Would you please move back a bit closer to the chair, please?
There are other things that are in the home you're familiar with. One of them I'm going to use right here. This compound is isopropyl alcohol. At home, you might have what's referred to as isopropyl rubbing alcohol, which is actually 70% isopropyl alcohol. This is 100%. I put some in that beaker, and this is a part of the demonstration. This is the contraption which is going to add to it. There's a wire gauze. It's like a screen on the top. There's a wire hanging down from here, and to the end of the wire there's a penny. And what we're going to do first is to heat the penny up. And you know, if you heat a metal real hot, it gets what we refer to as being red hot. And that's what's going to happen to this penny. It's starting red hot now. And if I take the heat source away, what happens is, of course, it cools down and it stops glowing within a short period of 2 seconds. Remember, now, in the beaker here, we've got isopropyl alcohol. We're going to warm this up a little bit. What that does is get more of the alcohol into the vapor state, which is where we need it for the demonstration. I'm going to warm up the penny again, and what I'm going to do is to drop the penny down inside the beaker which has isopropyl alcohol in it. I'm going to take the flame away, which is keeping it red hot. And what's going to happen is the penny down in there is still hot, and it'll stay hot for some time. There's a reaction which is going on between the isopropyl alcohol and the red hot penny. We call it a copper catalyzed reaction. We call this reaction as being an exothermic reaction because the reaction is producing enough heat to keep the penny red hot. The fact that the penny is red hot causes a reaction to go, so it's kind of going together there. It has to be hot to get the reaction to go. Since it's going, it's keeping it hot. And it'll go for some time. There are other things in the hole that you might be familiar with. You might have hydrogen peroxide in your medicine kit. If you do, you've probably got 3% hydrogen peroxide. And I'm going to use hydrogen peroxide, but this is 30%. You don't put this on cuts. You don't allow this to get on your fingers because it hurts. If you put hydrogen peroxide 3% on your fingers, it kind of bubbles up on a cut. It kind of bubbles up in, and the idea is to kill the germs. This will bleach your finger and hurt. We'll just put a little bit in this graduated cylinder. And along with it, another reagent, something that you're familiar with. Some are more familiar with than others. And mix it up. There's a solution then of hydrogen peroxide and soap. To make it a nice looking demonstration, I'm going to add a little bit of food dye. Just a little bit down the side is enough. And I'm going to set it on, this is called a watch glass, or an elephant contact lens. I'm going to put it on that and add one last ingredient. And there's going to be a reaction. There's energy in this system too. There's energy in a lot of things. And this is a source of energy. Remember when I ate the banana, I said I was going to take 2 breaks? This is another break. And what I'm going to do, again, is to run a reaction for you. I've started a reaction. Actually, it's starting. I'm grinding it up. You might know that chemical reactions go faster if they're more finely divided. That's where we chew things up. I've mixed it up. This saliva, it's down to my stomach, just about all down my stomach. Enzymes and juices and all those things. And what I'm going to do is to get the food energy out of that piece of cake. This is about the same size. And I'll have to go around here. You remember early in the show, we talked about making liquid oxygen from gaseous oxygen. What's that? And now we're going to see liquid oxygen. And it's cold, of course. It's got a blue color associated with it, and the frost and stuff in there is probably moisture leaking into the container. Well, this is a Dunkin' Donut, I guess. We're going to dunk it down into liquid nitrogen, and you know what's going to happen. This is hot. This is cold. And what's going to happen is it's going to cause it to boil. And the first thing that's going to happen is it's going to boil and cool the sample of donut down. It's going to cool it down to its boiling point, and when it settles down, it's down to the temperature. Now, I think it's pretty well done. Put that on this gadget right here. And I'm going to douse it a little bit with oxygen to make sure that there's as much on there as we can get. And then we'll ignite it. And there's a piece of donut which is showing you the calories that are in a itty bitty piece of donut. Now that's most of the donut is right there. And perhaps that gives you a feeling for food energy, how many calories there are in food. Okay. Next we have another clock reaction, and this is perhaps the most sophisticated demonstration that I have here today. Clock reactions you're familiar with. You know that solutions are mixed together. It takes a quick period of time before you see evidence of reactions, and that's what's going to happen in this case. It's turned yellow, and then it's going to turn blue. This is called an oscillating clock reaction because, well, if you missed it the first time, we just gone from the mixed the solutions together, they were clear, then they were yellow, and then they were blue. I just cleared it up, made it yellow, and there's the blue starting from the top there. And it's kind of neater if we do it in a tube like this. You can see the solutions happen. Goes from clear to yellow to blue. There's the clear and the yellow. And there's the blue. It's called an oscillating clock reaction. All of the other things that I've done, I've mixed the things together and the reaction's been done. This one looks like the reaction is done, then it goes back to the beginning and it goes through the reaction again, it goes back to the beginning and goes through the reaction again. It's kind of like taking the log, throwing it on the fire, burning it up, and then somehow getting the same log, throwing it back on the fire, burning it up again. And this was first published back in 1951. That isn't too long ago. And the people that published it were, well, they didn't publish it in a reputable journal. It had to be published in an obscure journal because the real chemists didn't believe it could be done. And there it is. We're at the end of the show, and I'm going to, again, use things that you're familiar with. You're familiar with chlorine bleach. And one of the things that you're not supposed to do with chlorine bleach is to add acid to it. And I bet you can guess what this is. That's acid, and a little bit of acid in there is going to release the chlorine from the chlorine bleach. And then we give it a little bit of a swirl here. It's kind of yellow. In fact, you can perhaps see up in the top, there's kind of a yellow gas associated with it. I'm going to add to that some of this material. This is calcium carbide. Calcium carbide reacts with water, which is also in there, to form acetylene gas, which reacts with chlorine to produce a reaction. And I like to refer to this as being a patriotic ending. It's kind of like, this is, well, we might refer to this as being Patriot missiles attacking Scud missiles, and you'll see what that means in just a second. Does that look like the skies on television? And to end up here, we have a series of clock reactions, again with the patriotic ending.
Red, white, and blue.
And you know about clock reactions, you know that there's a change after a period of time. And to be a patriotic ending, it has to be the right system. And here we go. There's red, red, blue, red. The white ones are hard to see. Let me pick up this one. It's going to be later. It's kind of cloudy to begin with, but it gets more cloudy. Go. There it goes. Did you see that? It wasn't very impressive, but that's the best I can do. I hope you've enjoyed the show. I hope you've learned some things. Thank you for coming.
How about yourself? Yeah, I need to bring the kids. Oh, yeah. There's all kinds of kids here, all ages. There are even some that are. Isn't that right? There's kids of all ages here.
Might be some Fort Wayne teachers there.
Quite a crowd.
Did you get tired too?
Yeah.
Too long for you.
Yeah, Molly got tired too, but that's who was saying. Well, the kids just keep coming up closer and closer. Did they yesterday too? Still? I didn't, I thought you were a trip over it a minute.
It's an awfully nice place.
Well, I'll see you at home.
Okay.
You'll be home by now.
Well, last time we talked, it was
Every single one. You mean you go from over to 9? Okay. I want to stay there. Do we find Mom and the other kids? Okay.
I've known about these places where which I found astounding that she would say that, but she did.
Yeah, I've done a lot of places. They're prettier places. If you're by yourself, that's one thing.
Right.
Yeah,
We have for families, we have for stories.
Dr. Longroy, I think I have your picture, but why don't you step out front here?
You want me to do a jig or anything like that?
Oh, I think not. I just hope that I get. That's great. Appreciate that. I'm not sure that I'm doing it right, but I'm trying.